The James Webb Space Telescope, JWST, is stirring up the scientific community with groundbreaking discoveries, challenging our understanding of the universe's origins. As it completes its first year of operations, the JWST has begun revealing extraordinary insights about the earliest stars and galaxies, shedding new light on the infancy of the cosmos. These revelations are causing scientists to reconsider their models of the universe, prompting discussions about the accuracy of previous theories. The JWST, dubbed a $10 billion time machine, has been designed to capture the faint infrared light from some of the universe's most distant and ancient objects. Its mission is to probe back to the early stages of the universe, within the first few 100 million years after the Big Bang. In this period, the first stars and galaxies began to form, and JWST's detailed observations are offering unprecedented insights into this pivotal time in cosmic history. The telescope's findings are so remarkable that they've left researchers both excited and perplexed. For example, the discovery of unexpectedly mature early galaxies has prompted questions about whether these could be mistakes in the telescope's early observations or perhaps evidence of something more complex and unusual about the universe's formation. Could these galaxies challenge the standard cosmological models, or do they suggest that our understanding of the universe is far more intricate than previously thought? To understand the significance of these revelations, it's important to revisit our current understanding of the universe's origins. According to the most widely accepted cosmological theory, the universe began with the Big Bang. In the aftermath of this event, the universe was filled with a hot, dense plasma of particles that gradually cooled. Over time, electrons, protons, and neutrons combined to form neutral hydrogen atoms, and the universe entered a period known as the Cosmic Dark Ages. During this time there was no light, and the universe remained dark and quiet for millions of years. Eventually, the energy from dark matter, a mysterious, invisible substance that makes up much of the universe's mass, began to have a profound effect. Dark matter clumped together, creating dense regions that attracted normal matter, such as hydrogen and helium, forming the first stars. These early stars began emitting radiation, reionizing the hydrogen gas that filled the universe and marking the end of the Dark Ages. As the universe continued to expand, galaxies formed and grew, eventually becoming the cosmic structures we observe today. Edwin Hubble's groundbreaking discovery in the 1920s showed that the universe is expanding, and further observations in the 1990s revealed that this expansion is accelerating. This acceleration is thought to be driven by dark energy, an enigmatic force that permeates space itself. Astronomers have long sought to explore the early universe, and the Hubble Space Telescope made significant strides in this area. In 1995, Hubble captured images of a seemingly empty patch of space, revealing thousands of distant galaxies at various stages of evolution. In 2016, Hubble discovered one of the most distant galaxies ever observed, GN-Z11, which was formed only 400 million years after the Big Bang. Although this discovery was groundbreaking, it raised questions about how such a small galaxy could have formed so early in the universe's history. This is where the JWST comes in. As the most powerful space telescope ever built, the JWST is capable of observing even further back in time, providing a clearer view of the universe's earliest stages. Located 1.5 million kilometers from Earth, the JWST is positioned in a unique orbit, allowing it to observe the universe in unprecedented detail. Its massive segmented mirror and sensitive instruments are designed to study everything from distant galaxies to the atmospheres of exoplanets. Already, the JWST has exceeded expectations, uncovering galaxies that appear to be much older and more evolved than scientists anticipated for their age. These discoveries are reshaping our understanding of the universe and may force us to revise the current models of cosmic evolution. The insights from the JWST could offer new perspectives on the formation of galaxies, the development of stars, and the role of dark matter and dark energy in shaping the cosmos. The discoveries made by the JWST are just the beginning. As the telescope continues its mission, it will provide even more detailed information that could fundamentally change our understanding of the universe's history and the forces that have shaped it. With each new revelation, the JWST is bringing us closer to understanding the true nature of the cosmos, and it may ultimately lead to a revolution in our view of the universe and our place within it. Scientists use a form of the Doppler effect to measure the distances of astronomical objects. This is similar to how the pitch of a siren changes as an emergency vehicle moves toward or away from you. The pitch increases as it approaches and decreases as it moves away. The farther a galaxy is from us, the faster it recedes, stretching the light and causing a redshift. The degree of this redshift is measured using a value known as z, which indicates how far the light has traveled to reach us. One of the first key discoveries from the James Webb Space Telescope, JWST, came from MIT astronomer and his team, who used a search algorithm to identify a galaxy that appeared unusually bright and distant, now named Glass Z13. Initially, this galaxy's redshift was measured at 13, indicating it was farther than anything seen before. However, the redshift was later recalculated to 12.4, renaming the galaxy Glass Z12. Other astronomers analyzing different JWST data have found redshift values ranging from 11 to 20, including a galaxy, CRS 1749, whose light seems to have traveled 13.7 billion years, just 220 million years after the Big Bang, a mere blink in cosmic time. These observations have prompted some researchers to question the lambda cold dark matter, lambda CDM model, the current leading theory of cosmology, as it seems inconsistent with these findings. According to Chris Lovell, an astrophysicist at the University of Portsmouth, massive galaxies shouldn't have formed so quickly in the early universe, as they would need more time to form stars. In a study published in November, scientists analyzed simulations of the lambda CDM model and found that JWST's early bright galaxies were larger and more massive than those predicted by the model. However, not all scientists are convinced that the lambda CDM model is being broken. Some argue that the lambda CDM model's predictions are not always definitive, and that dark matter and dark energy remain poorly understood. Additionally, the first years after the Big Bang are difficult to simulate accurately in computer models. Another challenge is the uncertainty of determining the exact distances to galaxies, as the redshift value can change with more accurate measurements. In fact, the redshift of some high redshift galaxies has already been revised. For example, CRS 1749 was originally thought to be an ancient galaxy, but is now considered part of a galaxy cluster with a redshift closer to 5.3, significantly lower than its initial estimate. Spectroscopy, where light is split into its components, offers more precise measurements and confirms redshifts for several galaxies, although some high redshift candidates still need further analysis. Astrophysicist Victoria Straight of the Cosmic Dawn Center in Copenhagen believes that more accurate measurements may reveal that some of the high redshift galaxies will hold up. Meanwhile, researchers are trying to reconcile JWST's data with the lambda CDM model. One idea is that the first stars, known as population 3 stars, could have been much larger and more luminous than modern stars. These stars, composed solely of hydrogen and helium, would have evolved differently, contributing to the unexpectedly bright early galaxies observed by JWST. Another possibility is that a slight adjustment to the lambda CDM model could account for these early galaxies. If the universe is expanding faster than previously thought, an updated value for the Hubble constant, the rate of expansion, could push galaxies further away than earlier estimates. This wouldn't be unprecedented, as the Hubble constant has been revised several times since Hubble's initial estimate. A more drastic solution would involve a complete overhaul of the lambda CDM model, perhaps by adding new particles, such as sterile neutrinos, which don't interact with regular matter. Such theories could be tested by looking for evidence in the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang. JWST's continued observations may provide new insights into these ideas. Richard Ellis, a cosmologist at University College London, suggests that JWST's discoveries are just the beginning. As the telescope delves deeper into the early universe, astronomers eagerly anticipate new findings that could dramatically reshape our understanding of cosmic history. JWST's ability to peer so far back in time opens windows into the formation of galaxies and the first stars, providing vital information that could challenge existing theories of dark matter, dark energy, and the processes that shape the universe. Among the most intriguing aspects of JWST's discoveries are the detection of galaxies at extremely high redshifts, suggesting they existed when the universe was only a small fraction of its current age. These early galaxies appear surprisingly large and evolved, raising questions about how they could have formed so quickly. Some researchers believe these galaxies could be remnants of stars that formed in a fundamentally different way compared to those seen in today's universe. JWST's observations aren't limited to distant galaxies. The telescope also studies exoplanet atmospheres and provides detailed views of objects in our solar system. Every new dataset helps astronomers refine their models of planetary formation and atmospheric conditions across different periods in the universe's history. Looking ahead, scientists expect JWST to make even greater breakthroughs. Its ability to capture faint infrared signals promises to uncover more secrets of the universe, from the earliest galaxies to potential signs of life on distant exoplanets. As JWST continues its mission to explore the universe, it holds the promise of advancing humanity's understanding of the cosmos, from the Big Bang to our place in the vast expanse of space.